Hello everyone, welcome to another session of Learning Glass. Today we'll do some more stuff. In this class it's called Scalable Manufacturing of Emerging Technologies. So we've been doing a hodgepodge, different topics, different engineering topics, different science topics, different business topics, different everything. Today we're going to talk about bioengineering in a very simple, under very simple assumptions. We'll talk about bioreactor design or simple analysis of a bioreactor. What is a bioreactor? It's a chamber that you use to make like microbial things or pharmaceuticals. In this case, it's to grow, to do cell culture processes in a reactor, and you can do this in the lab, or you can do, and it's done in the large scale, industrial scale. So to start, let's talk about microbial, meaning microbes, germs, or different applications of this microscopic life. Microbial growth kinetics, meaning if you start with some amount of microbes, what is the time scale? What is their growth rate? How fast do they replicate? That's what kinetics means. What is the time dependence? The change with time. That's what the study of kinetics is. It applies to chemistry, and from chemistry it branched into the rigorous calculation of microbial growth, and it's also related to transport of mass and energy. You can think of heat transfer as kind of like a energy kinetics. Okay, so one way to look at this process is that if you were to have cells in a culture, in a petri dish, what you do is you can see how this relationship with the number of cells with time is, typically on the scale of hours. There's some characteristic features of this growth and death of cells, the number. So if you take these cells, so if you have like a starter, what's called the inoculum, meaning you inoculate this with life, little microbes. This is like your starter set of cells, plus some medium, which is the nutrients that this needs to live and grow and replicate. If you put this together, what you typical properties that you would see was that at time zero, the number of cells would stay constant for a little period. The period depends on the conditions. And then, so I guess what this period is called stasis. That's when these cells adapt. They get their bearings. They just first adjust themselves a little bit, this first population. Then these cells exponentially grow. They're happy, they're stasis, and then they blow up exponentially into exponential growth. And then they slow down a little bit, and then they reach some equilibrium, it's called a stationary period, or homeostasis in like other settings, and or steady state. And as you can imagine, eventually they're going to die. I mean, the conditions are no longer sustainable. Some imbalance in the nutrients versus the waste. You know, it's a process with some intake and some outtake. That outtake is not good. You need to flush that away. And so there are going to be very reasons why these will die off. But typical time scale is like, okay, 15 hours for stasis. That's not, it depends, of course. But it can be like 24 hours. You can reach this stationary period, and then death after that. Sometime after that, depends on the situation. So this is the stationary period, where the replication equals the death rate. And this is, decline of the population. And this is the exponential growth rate. The exponential growth period, it's where there's an excess in nutrients, you're not limited by nutrients, and no excess waste. These cells, they have these byproducts. If they saturate themselves in the byproducts, that causes a decline. But it's when everything is right for growth, they take off. And so this is in a this is like in a petri dish, a culture, closed batch system. You just don't keep it flowing, you don't replenish or exhaust, you just keep it in there. This is what would happen. And for this exponential growth, for exponential period, you can imagine what happens. This happens in chemistry as well, where once you form one, so this is one little bug, one little microbe, and then that splits. And if the conditioner is right, it'll split again. But because one microbe can split itself, it'll branch out. So I shouldn't make these different sizes. It's not the size, it's the number that's growing. Try to space it out. It's harder than I thought. So these all split, and each one makes two. And then each two makes four. So that's how what we mean by exponential. That's how it looks on the graph. But on the floor, when you're in the microscope, what you would see is that you start with 1, meaning 2 to the 0, and then that 2, you have the exponent of 1, and then that 2 gets squared, and then that 2 gets cubed, and you keep on growing, and that's how you branch out exponentially. And so that's what happens under microscope for microscopic growth. For chemical reactions, that happens in a lot of chemistry, where once you form one, that leads to some branching into some exponential reactions. And if you plot that on a graph with time, it'll look like this. And if you were to plot this exponential period, what you would get would be, for the exponential growth, it would be the concentration it's exponential growth, and then, so the concentration will change. The natural log of the concentration equals the natural log of the starting concentration, the starter inoculum, then it grows by some rate. Let's call it mu. So this will be the concentration over the period with time. Concentration, this would be the initial, and this is some growth rate. Here it's assumed to be constant, and that's 1 over second, and this is the time in this specific period. That's how the math would look. And that behavior, like I said, has other, that math model also works whenever you have this exponential growth in any situation. And one other characteristic math that if you were to integrate this equation, you would get this so-called first order kinetics relationship, where the time change, the rate of time of this concentration with time is the related to the rate times the concentration to the first order, to the exponent of 1. That's how that math works in terms of the time rate of change. So that is one example of first order kinetics, and this was observed experimentally in the 40s just by counting them under the microscope with time during this growth period. And it's not only specific to microbes, but it happens in this math model, works in a lot of cases. This exponential growth due to some chemical reaction, going from consuming the starting reactants to products. And what happens is you branch out like this. So that's one thing. Okay, so now let's apply this to large-scale production of microbes using some simple analysis to show how you can build a bioreactor based on this model. So in this situation, this model works neglecting the concentration of the food, of the nutrients. This is a pretty accurate model. And where the nutrients come into play is the acceleration and deceleration here. That can modify the equation in terms of how to consider this nutrients. But once you're in this exponential growth, you can ignore that. And that's what is kind of how this next analysis works, where if you're going to have large-scale production, which is what this class is about, scalable technologies, which is not a new technology, but it's still very useful for when we develop new, bioengineering techniques, we can use these reactors to scale them up. So for large-scale production, Petri dish is not good. What you want is a continuous reactor, meaning instead of having a huge Petri dish in a factory, you want just a constant flow of in and out to pump out these microbes, not bake them in a big Petri dish. So that's batch versus continuous. This is batch. Batch is useful in some cases, but most of the time when you're talking about large-scale production, you want continuous assembly line flow. So this is continuous, if I can learn how to spell. Continuous, change color here. Continuous reactors are more productive. More productive, it's all about productivity, efficiency. That means more money. Are more productive. So a common design in bioreactors, it's called continuous. Let me erase all this. So we're doing large scale production. We want continuous reactors. So how do we do that? Well, common design, it's called continuous tank stirred reactor. So it's a tank, but you're constantly flowing in and out. So it's a continuous process. Get some vibrancy here. Continuous, there we go, continuous tank stirred reactor. Continuous tank stirred reactor, aka CSTR. So a common design is a constant continuous tank stirred reactor. So let me draw one here. So you have a tank. Here's my tank here. Then, since it's a bioreactor, most of the times you need, you always need mixing. So it's going to have some impeller, some agitators coming down. So let's say this is the agitator, stirrer. They're more complicated than that, but I'll just draw like this. And if it's aerobic, you're going to need to feed it to keep the water, the oxygen nice and saturated, to keep it happy. So there would be some inlet for to pump in gas. So it's a liquid. This is a continuous tank. And these bioreactors, they work in a medium. They need some nutrients, and the transport is easiest if you have some water that it's submerged into aqueous system with some nutrients. So it's like, this is bio stuff, so it likes to be nice and immersed. So it's a tank most of the time. So that's the liquid level. And then you need to, if it's aerobic bacteria or aerobic microbes, you need some oxygen. So if you don't it'll work best if you just have this constant flow of plenty of oxygen. So what you do is you feed this gas. It can either be oxygen, or it can be air, or it can be some mixture of something. And it goes into the liquid, and it's called a Sparger process, where it kind of looks like some way to introduce this, to disperse the gas into the water. So that's what Sparger means. So that's, you shake it up, you stir it, and you have it nice and saturated with oxygen. Then you feed in nutrients. So this would be the medium, like keeping the medium happy, nutrients from feed reservoir. Then, I'm simplifying it here, but at some point, somewhere in this design, you're to have a mechanism to pull out the products. So it's continuous. In a steady state in the best designs, so the volume and the nutrients you pump in is balanced to keep it operating such that you're always going to pull out a steady amount of products. So this would be the culture, the finished culture to the product reservoir. So the product is a culture, and then you're pumping it out constantly in a continuous fashion. And then, depending on the design, or in most cases, you need to monitor and regulate the temperature, the pH, meaning how much acid or base in terms of either the hydrogen concentration or some other measure, but pH is important for biological processes, and oxygen. Depending on the situation, you need to maintain these at certain levels to keep the bioreaction happy. And this is pretty complex because there's a mixing problem and basically a mixing problem, which is mixing with what? You need to mix the starting cells with the nutrients. You need to mix the starting cells with the right gas mixture, the right dissolved gases that's in this liquid. You need to keep the temperature constant throughout. You need to keep the pH constant throughout. So there's a mixing design that it needs to do, which can be a mechanical problem, because you can imagine if there was not even around here. That's why the stirring is important, because you need to do something to actively keep everything mixed. So that's what the stirring is about. And if you don't do that, you can imagine pockets of dead zones or pockets of rich zones, which is not ideal, because you want a consistent product outside without any weird pockets. So all of this is important in terms of the specifics of the design, but we're going to analyze this under very simplified assumptions. So what we're going to do is, instead of having this Petri dish batch version, we're going to consider what is the balance between what comes in and what comes out, and we're going to have a different behavior. If it's steady state, it's not going to have this up and down nature. So let's talk about that. Okay, so first thing is that when it's flowing in, doing its thing, and then flowing out, it can go through it. If it's uniformly mixed, it's like an average, a good average. So the residence time is a way in chemical reactors, any process where you're trying to control some process in a reactor, you can characterize that by the residence time. In a simple geometry, it'll be simply a simple residence time would be the flow rate going through divided by the volume. So if it's volumetric flow rate, so the volume of this reactor over the volumetric flow rate So in this case, it's a little bit oversimplified, but it's a pretty good way to quantify this. If there's a certain volume of liquid and it comes in at a certain rate, comes out at a steady rate, same rate, and you know the volume, then the time spent within here is the ratio of the volume to the flow rate. So that's a residence time, and that's the time that that you have in this certain setup to get to your products. And of course, if you don't have enough time, it'll affect the results. If you have too much time, you don't need that much of a reactor. You want to optimize the residence time, and that depends on all these factors: the temperature, pH, and the details of the bio process you're doing. But in bio analysis, in bioreactors, they typically talk in terms of dilution time. So dilution time is another way to describe the residence time. It's D equals 1 over T, residence time. So D over the so what that is saying is that it's the volume flow rate over the volume. So it kind of tells you, depending on how much you flush this out, where you start with a new set, with a new situation. And that's another way of saying the residence time. It's kind of like the time scale where you cycle through a new set of conditions. Okay? So, with those definitions, and then we're going to talk about some more assumptions here. Like one assumption we can say is that, I guess let's say them here, that there's a conservation of cell mass and nutrient mass because what's happening is this is sterile nutrients. There's no new cells coming in, but it's saying if you have some starter cells and you reach steady state, once you reach the steady state, the conversion of nutrients to waste is offset by the conversion of cells. So that all balances out. That's one assumption. Another one is that you don't have any cells in the nutrients, so the nutrients are sterile, so there's no source of new cells in the feed here. They all started here and are reached some steady state. And of steady state, you reach the steady state. So this is after inoculum. So inoculum, the starter, the inoculum is loaded, and then this idle period, this what is it called, stasis, is finished, and then it's an acceleration and deceleration, so that you're reaching some steady state of what comes in equals what comes out. And all of this reactor works nicely such that the temperature is evenly distributed, the nutrients are evenly distributed, all the gas is evenly distributed. So it's perfectly mixed, which is not easy. You get a good agitator, a good Sparger, temperature controlled and such. And you need to regulate the pH if you need to. So that means it's kinetically controlled, meaning the only thing going on is this reaction here, not any mass transfer that you need to, the cells need to travel somewhere to meet with the nutrients. That can happen, but that's a different regime. This is, instead of having mixing control, it's reaction control. That's what this means. I mean, it's determined by the reaction. Kinetically controlled means that the kinetics determine what's happening. Mixing controlled or transport controlled means that the mixing determines what happens. Okay? And then this is a simple nutrient. It's going to be a complex mixture in real life, but we're just saying that it's only one factor that affects this nutrient. It's a simple single nutrient. Okay. So for all those assumptions, some of them, this is how we operate. If we have an ideal reactor, which it's not always perfect, but in large-scale industry, of course, we want to have a good mixing. We want to have a steady temperature, steady oxygen. So we strive for this, and this is reached for the most part. It's never perfect, but that's what they're designed for. And we operate at steady state. A lot of industrial scale processes, it's all about steady production. So they optimize the processes so that they operate where you can use a balance between what comes in to what comes out to reach some steady state of production. and the nutrients, you can sterilize your nutrients. So what you do is you do a balance. So so the cells that come in, you know, or the cells coming in, this culture, the cells in minus the cells out plus the cells produced equals 0, steady state. That's 0. If the nutrient is sterile, then there's no cells in. So that simplifies this analysis. What you're saying is the cells coming out, where they come out is here, that balances out what gets produced, what replicates inside of this reactor. So if we were to draw that out, that would be, let's call this F here. There's a flow rate F coming out, and that has a concentration. So the cells coming out is the flow rate of the mixture coming out times the concentration of the cells coming out plus the rate that are produced. That is given by these first order kinetics. We're assuming we're in this steady state exponential growth where it's not that they are living and they're dying. That's not how we design this reactor. We don't want the cells to die in here. What we want them is to keep on replenishing things such that it's always a balance between what's being produced and what's getting taken out. So it's not in that stationary period where in a petri dish it's not happy because at one point it was really thriving and growing until they reach their saturation and there's some balance between life and death. That's not how we design our bioreactor. We want to have it where everything is thriving and there's an excess of products and not an excess of waste. That's what we do. We keep on replenishing this to both keep it at a continuous output, but also we can keep the cells happier that way as well. They'll always be thriving. So that's where these first order kinetics come in. So we're going to apply that here. The cells produced is related to basically the cells produced over time is the growth rate in this first order regime times the concentration. So that is, so that would be the volume. I skipped a step, spoiler alert there. What is produced is the volume in the of the liquid, the volume V times the rate of change the cells produced. So so this is, let's say that this is centimeter cubed per second. This is a number per centimeter cubed. And this is the outflow, as we said here. And I'll just erase that because that's how we did the balance. It's what's coming out. And then this is centimeter cubed. And then the number of cells produced with time per second. So that's how this balance works. And so this would be the number per second. This would be, the X is per centimeter cubed. This is a concentration. So the number per volume. This is number per volume. So that would cancel out here again. And so it's at steady state, so this is 0. So going back to this first order, we can plug in our definition of, our time rate of change. If it's first order kinetics, it's related to this rate coefficient and the concentration. So that would be, so we have the units. Let's erase the units. It will be Fx equals V mu x. So that is simplifying this. So that what we see here is the concentration drops off. Okay. And then if we were to take the ratio to isolate mu, mu equals the ratio of the volumetric flow rate over the volume. And that is the dilution time. So what we get is an interesting result. That under a simple analysis, which for the first order is how we're designing it. We want perfect mixing, we want a steady state, we keep the nutrients sterile, there's no cells, a source of cells coming in, and we can express the volume, the residence time by the dilution time of a simple in and out and the ratio of the volume to the flow rates. What that says is that the rate of growth, rate of replication mu equals D. So it's related to the residence time. So that's pretty interesting. When you have first order kinetics, so in an ideal reactor, you get a very simple result. What that's saying is that ideal culture replication rate in a CTSR can be controlled by the dilution rate, by the residence time. That's just the mass balance. And so, yeah, you can use that. You can use this in reactor design. It can be, yeah. If you're designing in a reactor for a certain rate, you can start off with this simple analysis saying that if I know I need this production capacity in my large-scale production, the CTSR is a common tool for that. And under these ideal conditions, if I want this rate of growth, that's simple, of course, because these microbes are very finicky. You need to have all this other factors. But on a first order, you can say, using this as simple analysis, that based on the residence time, I can roughly control the rate of growth, rate of replication. And you can also use this in research. For research, if I have this simple relationship, you can isolate mu to study culture behavior, to study this culture process. So you can change the temperature, you can change the pH, you can change the nutrients, and if you make this relationship easier, you can more effectively pin down what's happening. Okay, so that is a very simple analysis, but very powerful, and a very definitely the way to start this type of design when you're trying to design these bioreactors. And again, we would imagine that these microbes are very finicky, very sensitive to a lot of parameters. So you need this temperature, pH, and oxygen control and such, and mixing, good mixing, but also chemical reactions. Many chemical reactors are CTSR, and many chemical reactions are first order, and all chemical reactors for the big industrial scale are steady state. So this similar math comes into play as well. Okay, so that's all I had today. Thank you. I'll see you guys next time.